Good morning, everybody. Here it is, another Friday. Time for another video. This week, I really wanted to talk about space-time and how that developed. Uh, I promise you, we're taking some very tiny baby steps. And this is just too big a topic to try to cram into one video, and so we may cover some other things at a later date. But this is going to be very tiny baby steps. Still, you better hold on to your seats. Space. So let's talk about space a little bit. First of all, we have zero dimension. So there it is. You probably missed it. Zero dimensions, a single point, a singularity, if you like, you can call it that. There's nothing else. You can't do a graph. There's no movement. There's nothing to measure. And food for thought. What if this is the start of the Big Bang? Zero dimensions. Next is one dimension. We have just a line, one single line, infinity, left to right. We have some artificial constructs that we've made for reference and measurements. So you'll see maybe like a yardstick or a meter stick has a 0 point and has markings for parts of inches or millimeters, or whatever you might want. The 0 is a reference point. Could be anywhere along the line. Just stick one on there. To the right of the 0 point is positive numbers. To the left of the 0 point is negative numbers. Hopefully you've all seen this and you have some idea of what a single dimension looks like. Now, two dimensions. We're moving up in the world here. Two dimensions. So now we can have a flat, infinite plane. Lines, curves, circles, shapes. You can think of, any shape you can think of. So we have up, down, right, left. We have angles, degrees or radians. And now we can talk about number systems, and also primitive operators and properties. And some of this I'm not going to go into. If you guys want to talk about number systems, we can do that later. So the first thing developed was counting numbers. All of you know how to count, I think, since about age 3. 1, 2, 3, 4, 5, counting numbers. Next is natural numbers. The natural numbers include 0. This may surprise you, but 0 came later. Back in Roman times, they had no idea of the number 0. If they had 2 apples and they gave away or sold 2 apples, then they were out of apples. They didn't think of 0 apples. Next was real numbers. Real numbers are like fractions, the ratio of any two natural numbers. You can say the ratio of 2 over 1 to get the natural numbers. So real numbers include all the natural numbers plus ratios of natural numbers. So 0.2, 1 over 3, anything like that. Irrational numbers are everything that's not a real number. And by that I mean not in the set of real numbers. I don't mean they're not real. So we have pi, e, some of you may know what e is, square root of 2. There's lots of real numbers. In fact, an infinite number of real numbers. We can talk about imaginary numbers and complex numbers. Those kind of go together. Complex numbers are every conceivable number expressed as a real and then a real times the square root of -1, where the square root of -1 is often referred to as I. And then we had properties which are like you can't divide by 0. 0 times any number is 0. You have the commutative property, the distributive property, on and on like that. So now that we have all the numbers we can think of, there are functions. We can have 2D graphics. You might have an Excel spreadsheet with 2 columns of data of any length, and time can be one independent variable. We'll talk about that a little more. You could have a single photo, which is a 2D representation, a single point in time. So you take a photo, it's a 2-dimensional representation. And then just like 1 dimension, we've added artificial constructs for reference and measurement. So you often see the 2 axes, x and y, they cross at 0, the origin. That's a reference point. You might have a reference line across there, like -1 or 3, and those are lines that are used for reference. You have measurement, just like you do in 1 dimension. The positive numbers are up and to the right. Negative numbers are down and to the left. So that's reference and measurement. Here's a little joke here. I says, be rational. Pi says, get real. So continuing talking about space, now we have 3 dimensions. We can represent the real world in a single instant in time. Anything represented by x, y, z, or length, width, and depth. Um, you have 3 axes now. So anything that can be measured as length, width, and depth. So you pick up a rock and it has length, width, and depth. Um, 3D photos, we've seen like whatever those things are called, those little view masters, virtual reality, holograms, sculpture, uh, and then tangible objects, things that you can touch with your hands and pick up. Those are three-dimensional. 3 dimensions can be expressed as 2D with added color or movement or perspective. You guys that are obsessed with perspective. So an artist can draw a painting with perspective. That's 2D, 2-dimensional with added color, and can represent 3 dimensions in a 2-dimensional painting. Again, you can have an Excel spreadsheet. You use 3 columns of any length, and that'll give you 3 dimensions. Ancient Greeks and Romans thought if all tangible objects, things you touch, consist of a length, a width, and a depth, then the earth itself should be the same. Objects in the heavens were seen to be 3-dimensional. The moon, the different planets that they could see, and on and on. So we see 3 dimensions now for real tangible objects. Once again, like I've said, we added artificial constructs for reference and measurement. Maybe initially we thought of the earth as sort of the origin, the center of things, because that's the origin of where everything we knew came from. We found out that using the earth for an origin reference didn't work as well as using the sun as a reference point. And so the sun became the center of the solar system. And then we advanced from there. So we learned about galaxies, the center of our galaxy, and those kinds of things. So you look down at my drawings here. On the left is 3-dimensional space. You can see the 3 axes all at right angles to each other, and I think that's important for measuring and observing 3 dimensions. In the center here is a 3-dimensional graph of a surface. You see the functions for X, Y, and Z. And then they plot the surface. I used to do a lot of this when I worked for NASA, observing 3 dimensions, 3 different variables, and actually they show you a 4th variable, which is the color. So, however, we're still talking about actually a 3-dimensional space. I also wanted to show you a little bit about time. So I have this little video here. If you watch for a second, you can see this graph growing, changing, and this also was some things I did for NASA, where you monitor your 3 dimensions of data with a time element, and so I thought that was important to show you. Up here on the left center, I know we're all freaked out here about gravity and how all this stuff works, and we'll talk about that in just a minute. At the top left, all it does is, all I do there is show the different planets and how they're three-dimensional spheres, and so there you go, 3 dimensions. So what happens after 3 dimensions? We talked about 0, 1, 2, 3 dimensions. What happens when we have more than 3? So those of us looking at numbers, we now have time added as a dimension. We've always thought of time as unidirectional and linear. There might have been, we can call it a beginning of time at the Big Bang. We could call that the origin. And then we have all positive numbers of time moving to the right. So we do have reference, that origin point. We have other references. The point where BCE turns into AD, that's a reference point. The death of Isaac Newton, that could be a reference point. All kinds of, we can add these references wherever we like. There is measurement, so we have seconds, hours, days, months, years, and on and on. So we do measurement of time. But these are all artificial measurements. They're used strictly just like in 2 and 3 dimensions. We have measurement of time, and we might have this little stick up here for time that has measurements on it, just like we do for 2 and 3 dimensions. So often we have more than 3 columns of data which need to be represented. We can use color and or time to represent more than the 3 spatial dimensions, and I kind of already showed you data moving through time, and data with color as a 4th dimension. And I wanted to stop here just for a second and say that time can be used as an independent variable, and it is used for many analyses when you're talking about variables that change through time. So you have, some variable that you measure, and and that variable is dependent upon time, which is your independent variable. And you can see here on the right, this is short graph of the stock market. the stock market is very, very concerned with trends and highs and lows. They may have reference points. The year 2000 could be a reference point, and then they look at trends of data. There are analyses you do, time series analysis and so forth, that all depend upon using time and the references and measurements that we do. So, however, just like I've heard one guy tell me that he plans on using 22 hours to represent a day and 90 minutes for an hour. I told him that's fine. The problem with that is that you'll never be on time for your meetings. So we use these measurements and these references for a reason. So space-time. Space-time is 4 dimensions or more. I watched a video yesterday about more dimensions, and I'll put that link in the description because I thought it was a very good introduction. So as we've progressed now, so we started with 0 dimensions, 1, 2, 3. We had added time as a 4th dimension. And so great minds began to think in these terms to add to where we've been before. The one thing you will always find about science, which certain conspirators that we won't mention, flat earthers, you can't just throw out things and then add back in different things that you can determine. So great minds started with these 3-dimensional space plus time and began to add to that and say, you know, where can we go from there? What if there were more than 3 dimensions and we just can't observe those dimensions in our day-to-day lives? I know a lot of people have trouble thinking in those terms, but it's possible. And remember that these are much greater minds than just your average Joe or Josephine. And then time is its own dimension. So what about time? What if time is multidimensional? What if we have 2-dimensional time? What if time is not linear and began with its origin at the Big Bang? What if it's an infinite line extending both directions and the Big Bang is just one of our reference points? Why does it have to be uniform in its speed? Again, we have our artificial constructs that we've added, but maybe time doesn't respond to that. Maybe it's speeds up and slows down and whatever. So the same thing, light, that's another intangible that we've always thought of as linear and unidimensional, and uh, uniform speed. So what if, like time, light is not linear and not uniform? Uh, you know, there's possible that light speeds up and slows down due to, whatever uh, that might interrupt it. So, in added to uh, time and light, we could add gravity. So gravity is another intangible that we've always thought of as linear. Uh, we have, we have our gravity equations. We know that as things get farther apart from each other, their influence of gravity becomes less. Uh, but what if it's gravity is not linear? What if it's not uniform? You have uh, all of these questions that where we're going now. These theoretical physicists are thinking of, theorizing, uh, and I know this kind of freaks people out. Just the thought of these kinds of things. Um, so this might blow your mind trying to put together all of these dimensions and time and gravity and all of this stuff. Uh, we have this new representation for gravity. If you look over here on the left bottom, you'll see this famous uh, gravity well. So the sun creates a great big gravity well, and Earth is moving around that gravity well, uh, and because of its speed or its velocity, it moves around and it doesn't sink into the gravity well. But what I want to tell you, so that you all know, this representation is strictly just a graph. It's a representation of some variables that we measured, and we have added artificial constructs and measurements that human beings use to think about and reference these variables. You can see that light is affected by these gravity wells, but it's all uh, theories or um, hypotheses that these theoretical physicists are hypothesizing. And so I don't want you to get all uh, freaked out by this representation, because all it is a representation of what they think might be going on. Um, so don't don't get too caught up in this yet, because there's still uh, possibilities of different things. So what have we learned? Come back down to reality, to Earth. So we have ancient scholars that created simple number systems with simple properties. These created more and more complex number systems. We have simple graphics. The graphics were made to represent our different dimensions Uh, that wasn't, they weren't the dimensions, they just represented those dimensions. The constructs that were added uh, simply helped us to visualize, to think about what these dimensions are. So we started with actually with 0 dimensions. We added to those to get 3 dimensions and then time. So many functions were created to represent real world problems, which extend to more and more complex problems. Remember what I told you before, everything in science is more and more complicated with each concept building upon previous concepts. So when we create these number systems or these graphics, uh, we've started with simple concepts and then built on those. And then the final thing that I would like to say is that we're standing on the precipice of mind-blowing, reality-bending concepts. This is going to be the next, maybe the next century. We're going to have some truly mind-blowing events. Returning to the moon, the Mars expeditions. We're just really pushing the bounds of what we've known in the past. So don't get all afraid and let's all hide under our beds and go back to the earlier simple days. We don't want to do that. We want to progress and learn, and I hope that you've caught some of that today. Here's another video I like, and hope you enjoy this.
Free will. It's something we've been grappling with for thousands of years, from Aristotle to Descartes, and will continue to grapple with for 1,000 more. Will we ever be able to make an AI that can think on its own? A second artificial version of me that is truly autonomous? A Robert that can actually think and feel on his own while this Robert here takes a nap? Impossible? Well, when you consider what human cooperation has already accomplished, a man on the moon, decoding the human genome, discovering faraway galaxies, I'd put my money on dreamers like Mark and Gil over the Earth is flat folks any day. Until then, nap time.
Here's you another cartoon. Here's the mom and dad saying, "Oh, look how cute. He has an imaginary friend." P.S. Square root of -1 is imaginary. And that's all I had today. I hope that you have learned something, and I've given you some things to think about. Try to imagine, and like I said, where we come from, how we built and learned and added to those concepts to get to where we are today and where we may get to in the future. I appreciate all of you that watch. I hope that maybe you'll get some of your friends to come over and watch. I do appreciate, I've been getting a few new subscribers, which is really exciting for a guy like me. So we appreciate you guys.